Okay, just a minute. Just give me a minute here. Okay, cool. So can somebody just confirm if I'm audible or not? You can just write it in the chat if I'm audible. Okay, a yes or a no maybe. Okay, all right, cool. So what we'll be doing in this whole masterclass is that we'll be covering 3 problems on trees, okay? And these 3 problems will be on binary trees. So what I'll be doing is, I think we've already shared the links with you guys. So what you can do is you can refer to these problems while I'm explaining them, okay? And there is just one thing. First of all, I'll be covering all of these problems independently, and after a certain point, I will be covering all of them together. So what I'll be doing is I'll be giving you one approach that can be used to solve all of such problems together. Okay. So the thing here is that with all of these problems that involve binary trees, you can have a lot of approaches. For example, if I give you 5 similar problems on binary trees, you can have 5 different approaches of solving these problems. But what you can do is you can develop a certain standard idea or a central idea by which okay, you can approach all these 5 problems together, right? So this is what I'll be doing at the end of this whole masterclass, right? So I think we can begin with the very first problem itself. So yeah, so the first problem is the left view of a binary tree. Okay, and yeah, let's just begin. So I hope my screen is visible to all of you right now. Can somebody just confirm that as well for me? My screen, my video as well. I mean, is everything fine or not? Just a very quick yes or no. Okay, I think there is some lag here. Right. Cool. So yeah, let's begin with the very first problem itself. The very first problem is the left view of a binary tree. Okay, so let me just open OneNote here and I'll quickly explain to you what this whole statement means here. Right. So if I give you any binary tree, let's say I give you this binary tree. And let's say we have another thing here. So what we need to do here is that we need to find its left view. So what exactly is a left view here? So if you have this binary tree, let me just put it here. Okay, just a minute. Let me open another page here. So if you have this as a binary tree, right? So what we do here is that we look at this whole binary tree from the left side. And which is the left side? The left side is this, right? So we try looking at this binary tree from the left side and we see which all nodes are visible to us. So if we look at it from here, then let's number these nodes as 1, 2, 3, 4, 5, 6, 7, 8, right? So the nodes that will be visible to us here are the node 1, because if we look at it, there is no node that is blocking this node from being visible, right? So node 1 will be visible. Then if you look at node 2 and 3, the third node would not be visible. Why? Because the node 2 is blocking this node, right? Now if you look at these nodes 8, 7, 6 and 5, sorry, 8, 7, 6 and 4, then the only node that will be visible to us is the node 8. The node 7, 6 and 4 will not be visible to us. Why? Because they're getting blocked by this node 8. Okay, and similarly for the last level, if you look at it, the node 5 will only be visible to us. There are no nodes blocking it, and this node is also not blocking any other nodes, right? So yeah, let me just list the left view of this tree here. So the nodes that are visible to us are 1, 2, 8 and 5. Okay, So just a very quick yes or a no if this is visible or if this was clear to you all or not. Like what exactly is a left view of a tree? Okay, great. So if any of you have any doubts in between, you're free to write it in the chat and I'll take these doubts as soon as possible. So what we'll do is we've already looked at one of the examples. Let's look at just one more example and then we can discuss the solution of this whole problem. So if you look at this tree, let me just reduce the size here. Okay. So it turns out that the size is not getting changed. But yeah, anyways, let's draw this tree here. Okay. So we have this node 1, then we have node 2, then we have node 3, and we have node 4 here. And another node that we have is node 7 at the bottom. And similarly for the node 3, the children are 5 and 6. Right. Okay. So let's discuss the the left view of this binary tree. So if you look at this whole binary tree from the left, the nodes that will be visible to us are node 1, node 2, node 4, and node 7. Right. So this is just I'm giving you an example of what the left view of a tree looks like. Now, what we can do is we can discuss the approach that we're going to use to solve this problem. So let's consider a very general tree here. Okay. So if this is our tree, what do we want? If you consider this whole tree in terms of the levels of the nodes, what are these levels? This level is level 0. This level is level 1. This level is level 2. This level is level 3. And this one is 4. Right. So what happens here is that for every level, we are only concerned about the node that is on the leftmost side. So if you look at these all these levels, the nodes that we will be selecting here will be what? Will be this node. Then we'll have this node, we'll have this node, we'll have this one, and we'll have this one. Right. So this is what we want in this whole problem. We want to consider this whole tree in terms of the levels. And for each level, we need to pick the node that is towards the left. Right. So is this making sense? Like, is the approach clear to all of you? How are we exactly approaching this problem? Okay, so is there a lag here? I am not sure. Okay, cool. So what we'll do is we'll discuss the approach here of how exactly we need to solve this problem, right? So there can be two approaches of solving this problem. We can do it either recursively or we can do it iteratively. So this is very common for all the tree problems, all the binary tree problems. You can approach them iteratively or you can approach them recursively. So whatever feels easier to you, you can approach that. You can approach the problem with that technique, okay? So what we'll do is we'll first of all discuss the recursive approach here. So if you look at this whole tree, let me make another page here. Let's keep it like this. Okay. So if you look at this whole tree and let's say I tell you that you need to go to every level and you need to first of all encounter the node that is towards the left. So what would you do? Wouldn't you do something like a pre-order traversal? Why? Because how does a pre-order traversal look like? It is something like you have a root, then you have the left, and then you have the right. So let me just name it like this, right? Right. This is what a pre-order traversal looks like. So what you can do is you can do a pre-order traversal, and for every level that you're encountering, you can pick the node that you're encountering the very first time. So let's say I tell you that you encounter this node on level 0. So you pick up this node. Okay. Now you move down and you come to this level. So what you'll have is you'll go to this node, right? And when you come to this node, what will happen is, you will be encountering this node for the very first time in this whole level. So if you consider this whole level, you will be encountering this node at the very first time. And this is the node that we're really concerned about. So what we'll do is we'll pick up this node. We'll pick up this node. We'll come back again to, what do you say, the left side of the tree. You come to this node, and this is again the first node that we encounter in this whole level. So we pick this up again. Similarly, we go here and we pick up this node. So what are the nodes that we've already picked up? We picked up this node, this node, this node, and this node, right? Now what happens is you will be going to the root, you will be going to the right side, right? So if you're here and you're doing a pre-order traversal, you will come here. Now, is this the first node that we're encountering in this whole level? No, right? So if it is not the first node that we're encountering, we won't pick it up. Similarly, now if we are done with this node, we'll go back to this node. Now, is this the first node that we're encountering in this level? No. So we'll again not pick it up. Now we go here, again we don't pick it up. We go here, we don't pick it up. We go here, we don't pick it up. And when we come to this node now, what you'll notice is that this node, okay, just give me a minute here. Right. So here what happens is that, when you come to this node, this will be the first node that you will be encountering in this whole level. So you pick it up again, right? So if you consider a pseudocode for this whole problem, we'll be having a recursive function, and we'll be having a function like this. Let's say something like this, and we have a node here. And what else do we want to have? We want to have the level, right? Because we need to keep track of which level we are right now into. Okay. And after that, what we can do is we can store another variable that is going to tell us which level do we want the node to be coming from next. For example, if we've already considered the first level, do we need to pick up right? So if we come to the first level and we've already picked up a node, do we want any other nodes in this level? We don't, right? So when we move to the next level, we'll pick up another node. And if we've already picked up one node in another level, do we want to pick up any other nodes? No, right? So if we have nodes like these, we will only pick up this node. We won't pick up this node, right? So in this recursive function, what we need is we need the node, first of all, we need the level, and we also need to check what is the max level that we've already considered, right? So let me just look at the chat to see if there are any doubts here. Okay, so maybe a yes or a no very quickly if you guys understood what I've told you till now. Okay, I think there is a lot of lag in the chat. So let me just look at YouTube here itself on my mobile. Okay, so seems like this is clear to you. I'm seeing a yes here. Please explain it once again. Okay, no problem. So let's just leave the pseudo code for now, because if you guys haven't understood the approach till now, there is no point in discussing the pseudo code right now. Okay. So yeah, there is just one doubt. One guy wants me to explain this again. So let's look at the tree again. Okay, let's look at this tree. And if I tell you that you want to find the left view of this tree, what would you do? You would start looking at this tree from the left side, right? So this would be the left side of this tree. You would start looking at this tree from the left side. And can you see that this particular node, let's call it node 2, and let's call this node 3. Can you see that if I start looking at this whole tree from the left side, node 2 is blocking the node 3. So node 3 won't be visible to us. Similarly, if we have this node as 4, 5, and 6. So what happens is that node 4 is blocking these nodes 5 and 6. So we will only be able to see this node 4, right? And if you look at this node, let's call it 7. So you can see it, but it is not blocking any other node, right? So in the left view of a tree, what you need to do is you need to consider these nodes level wise. And if you start considering these nodes level wise, you only need to pick up the leftmost node in each level. Right. So now is this clear to you? Okay, there is a lag, I think. But I'm not sure how to actually detect that lag or correct it. So what I'll do is I'll just continue for now. And if we have any major issues, then we can try debugging it somehow. right? So where were we? We were looking at the pseudo code of this problem, and let me just open Sublime here. This should be clear while writing code. And what I'll do is just a minute. I'll put it on Code Studio itself, right? So we have this whole function that we need to complete. Print left view of a tree. And what is the approach that we've discussed? The approach is that we'll be doing a pre-order traversal. We'll be doing a pre-order traversal, and for every level, we will be picking up the node that we're encountering the very first time, right? So what you can do is I'm just writing a very pseudo code here. So I'm not writing the whole approach here. So let's call this function some like this, and we have something like this. Right, and let me make it full screen here. Okay, so we have this function that we want to complete, and we're doing a pre-order traversal here. Just remember this. Okay, so what is a pre-order traversal? Pre-order traversal is root, left, and right. Okay, and what we need is we also need a vector here. Okay, maybe we don't need a vector, we just need to print this answer. Okay, anyways, so what happens here is that for every level we'll be picking up the node that we're encountering for the very first time, right? Okay, cool. So what we'll do is, first of all, if root equals to null, then we don't need to do anything, right? We'll just simply return. But now let's say we are in a particular level. Let's say we are in a level 2, and we have already considered nodes in level 1. So if we have already considered nodes in the level 1, and if we are in the level 2, so what does this mean? This means that we are encountering this node in this level for the very first time, right? So in this case, what we'll do is print the value and increase the max level by 1. Why are we increasing this max level by 1? Because we've already considered the first 2 levels, and now we need to consider the next level, right? We can only print 1 node in every level. Okay, so this max level has to be something like passed by reference, because we will be increasing it at every point, right? And okay, so let's just define an if else here. If level equals to max level, then we just print what can we print? We can print val here, right? Let's print it like this, and we'll also do what? We'll do max level plus plus, right? Otherwise, what we'll do is we'll just call this function again. Right, so this is basically like a pseudocode. I mean, I haven't considered the compilation errors here. I'm just writing it for the sake of writing it. Well, number of levels doesn't give the answer. Oh, so the thing is, we don't need to find out the number of nodes. We need to find out every node, okay, which we are getting in the left view of this whole tree. We don't just have to find out the number of nodes that will be there. So if you talk about the number of nodes, that will be exactly the number of levels. So that is like a good observation here. But apart from that, we also need to find out every node. Okay, so we need to print them. Okay, so just a very quick yes or a no if this first problem is clear to all of you or not. I mean, I'll just quickly show you the solution here. Right, so this is the solution that we have. This is, I think, the exact thing that I wrote. So we have 2 variables that we need to consider. We have the level and we have the max level. The level is telling us the current level. The max level is telling us the levels that we've already considered till now. Okay, so let me just write some comments here. Can I think I cannot. Let me just copy it here. Right, so let me just write certain comments here. We are doing a pre-order traversal. This is the part where tree has ended. This is the part where the tree has ended. This is just like a base case where we need to return. And just a minute, yeah. So if we have here, what does this mean? The max level is less than level. What does this mean? This means that the levels that we've already considered are less than our current level. So this means that if we are moving to our current level, this is for the very first time that we are moving to it. Coming to the level, let me write it like this, current level for the first time, right? And what did I tell you? If you come to a level for the very first time, you just print the very first value that you get. And which is the first value? This is the root right now. Why? Because we're doing a pre-order traversal. So we'll always encounter the left nodes first. Okay, so this is how this problem can be done recursively. So just a very quick yes or no if this was clear to all of you. I think I've already done the code walkthrough once again. Okay, cool. So what we'll do is now we'll look at the right view of this whole tree. And the great part here is that if you understood the left view of this tree, it is very easy to understand the right view of the tree. Okay, so let's consider the right view now, first of all. So if we have these nodes like this, something like this. So what will happen is you look at this tree from the right side now. Initially, we were looking at it from the left side. Now we'll look at this whole tree from the right side. So if we number these nodes, something like 1, 2, 3, 4, 5, 6, 7, 8, and 9. So can somebody tell me, like, I mean, if there is some lag in the chat, so I won't ask you to actually tell me the answer. I'll only explain it to you. So if you look at this whole tree from the right side, can you see that the node 1 is visible to us, right? So we'll write node 1. Now you look at this another level, which is 2 and 3. Can you see that only 3 is visible to us, but this node 2 is getting blocked by the node 3. So what we'll do is we'll print 3 again. Now we come to this another level and we see that 6 is visible to us. So we write 6, but 5 and 4 are being blocked by 6, right? Similarly, for the next level, we have 8. And for this level, we have 9, right? And let me just pick up another case here that they've given in this whole question. So yeah. So the tree that we're getting in the sample here is this. Right. So can you see that if you look at this tree from the right side, the nodes that will be visible to us are node 1, node 3, node 6, and node 7. Right. So is this question clear to all of you right now? Okay, great. So there is a comment by Thunderlip, I think. Yeah, that is how you pronounce it. So he's telling us that we can do it using post order now. So this is a great observation. Like I said, if you've understood the left view of this tree, you can very well understand the right view. So initially in the left view, what were we doing? We were doing the pre-order traversal, right? We were doing the pre-order traversal. And what is the property of a pre-order traversal? The property is that for every level, you will encounter the left node for the very first time. Like if this is a level, let's say this is something like this. So what happens is that if you do a pre-order traversal, you will always encounter the leftmost node in every level first time, right? I mean, if this is node 1, this is node 2, this is node 3, this is node 4. What happens is that you will first encounter node 1, then you'll encounter node 2, then you'll encounter node 3, then you'll encounter node 4. Okay, this is the property of a pre-order traversal. Similarly, if we talk about the post-order traversal, what is a post-order traversal? Post-order is, just a minute. This is, sorry. We won't be doing a post-order traversal, sorry. What we'll be doing is we'll be twisting the pre-order traversal just a very little. Okay, so initially what we were doing a root, left, right. Cool. Now what we'll do is we'll do root, right, and we'll do left. Why? Because now we want to go towards the right side. And this is very important that the root comes before your left and right. Okay, let's understand why the root needs to come before left and right. Let's say I give you this tree, 1, 2, and 3. So can you see that if you look at this node 1, this has to be printed before node 3. So the root has to come even before all of its descendants, right? So first we'll have root, then we'll have right, then we'll have left. Okay, and we'll be doing the exact same thing. Okay, we'll be doing the very exact same thing. Yeah, so Ayush Yadav has suggested that we can do the level order traversal and store the rightmost node of each level. Right, Ayush, that is a very great point. We will be coming to this whole thing at the very end. So after I'm done explaining all these 3 problems to you, I will be giving you a very general approach that you can use to solve any such problem. And the idea that you've just suggested would be the core idea when I would be explaining to you that. Okay. So is this part clear to all of you that why initially when we were doing root left and right, why are we now doing root right and left? Just a very quick yes or a no. Okay. So maybe there is some lag again. But yeah, anyways, what I'll do is I'll explain you the solution that they've given to us in this problem, which is the right view of a tree. Okay. Yeah. So the solution is exactly the same. Let's copy it and paste it here. Right. So the solution is exactly same. The root is null, then just return from here. So they've also given us comments here, which is great. And now the thing is that, initially what we were doing was we were considering it like a variable that is passed by reference. But here what they've done is they've just passed a pointer to this variable. So it is exactly same. Okay, there is nothing different here. You can do it the exact same way as we had done it initially for the left view of the tree, right? So I think this should be clear. There is not much to explain after I've explained the left view of a tree. Okay, cool. So assuming that the left view of the tree is clear, the right view of the tree is clear, now we will be covering the top view of the tree. So now things get a little bit difficult. It wouldn't be very easy like it was in the left view and the right view. It will be a little difficult to visualize this top view. Okay, so can we start with the top view? If you guys have any doubts, let's first cover these doubts and then we can move to the top view. Okay. Okay, so I'm seeing a yes here. There is just one yes. If you guys have any doubts, you are free to write it in the chat. I would be happy to answer all of these. Okay, cool. So what we'll do is now we'll look at the top view of the tree. So it gets a little bit difficult now. It wouldn't be so easy compared to what it was in the left view and the right view. Okay, cool. So what I'll do is I'll just consider it like this. Let me pick up ruled lines here so that it makes more sense to all of you. Okay. Now, if you look at this tree, if you consider any tree for that matter, right. Now, the main reason why I actually considered it in the form of a grid is because we will be now looking at this tree from the top. Okay. So if you look at this tree from the top, let's say I tell you to look at this tree from here. So what are the nodes that will be visible to us? And what are the nodes that will be hidden from us? Can you see that for every line? Let's draw a line here. Okay. So I don't have a pen here right now, so it might be a little difficult to draw, but anyways. Right. So can you see that for these lines that I've drawn here, the node that will be visible to us is the node that will be at the top. For example, for the middle line, this will be visible to us. Right. And if you just take a step towards the right, which node will be visible to us? This node will be visible to us. And this will be hidden. This is hidden. Why? Because this is hidden from the first node. The first node is blocking this node. Right. Now, if we move to this node, there is no node that will be hidden right now in this whole line. Similarly for this node. Now when we move here, we'll be encountering this node, and the node that will be hidden is this one. So the red nodes are the nodes that we are not able to see. The white nodes are the nodes that we're able to see. Okay, sorry, this has to be red, right? Okay, similarly here, okay, how is it getting changed here? I'm clicking on the white node and right. So is this clear to you, like which are the nodes that are visible to us and which are the nodes that are hidden from us? Can somebody just confirm if this was clear to all of you or not? Right, exactly. All the boundary nodes from the top will be visible to us. This is a good point. Okay, I understand the question, but sometimes unable to write code for it. Any suggestion? Uh, are you talking about this particular question, or are you talking about questions in general? If you're talking about this particular question, I will be showing you exactly how to write the code. And later on, like after I've covered these three problems, I will be giving you a very general approach that you can use to approach all of these three problems. So you won't have to worry about how exactly to implement each of these. So can you quickly tell me if you're referring to this particular problem, or are you referring to any other problem, or like problems in general? Okay, in general. So I think what we'll do is we'll pick up doubts like these, which are a little different from what we are covering right now, at the very end. Okay. So if you can stay with us till the end, I would be happy to cover these doubts as well. Right. So I think the visualization should be clear to all of you now, like what exactly is visible to us when we look at the tree from the top. Right. So what I'll do is I'll just pick up another example here. Yeah, what we can look at this example, right? The example that they've given to us, this tree here. So if you look at this tree from the top, you first of all look at this node 1. If you look at this middle line, if you look at this line, okay. So the node that will be visible to us is node 1, and node 5 will be hidden from us, right? Now you move towards the left, you see that node 2 is visible to us and node 7 will be blocked. Similarly, you move towards the left again and you see that node 4 is visible to us and node 9 is getting blocked. Now you move towards the node 10 again and it will be visible to us, but there are no other nodes that are getting blocked now, right? And similarly, if you move towards the right, you see that node 3 is visible to us, but node 8 is getting blocked. And you move one step right again, and you'll see that node 6 is visible to us, but node 11 is blocked. Okay, cool. So just a very quick yes or a no again. Is this whole visualization and what we are actually doing in this problem clear to you? Because only then can we actually look at the section. Okay, just a very quick yes or a no if you guys are here or not. All right. Anyway, I think there is some lag in this whole thing where I'm not able to see comments really soon, but no worries. So let me just discuss the approach of solving this top view of a tree. Okay. Like breaking the left part of the tree for left, Okay, that's a very good point, Thandalip. What I'll do is I'll give you a case where this does not work. Okay, you cannot break the left part of the tree and the right part of the tree and solve them independently. This is very important here. Okay, so let us consider this example. Yeah, let's say we have something like this. Right. So okay, there is a 15-second lag. No issues. So can you see that you cannot just break the left part and the right part? Okay, you have to consider them. For example, if you start printing the top view of this tree, the top view would look something like this: 2, 1, 3, and 6. You wouldn't be printing 6 before 2, right? So if you break these left and right parts, if you consider them like this: 2, 4, 5, and 6, essentially what you would be doing is you would be printing 6 before 2. Okay, so this is very important, and this is a very valid doubt. You cannot just break the left and the right part. This is very important to understand. Okay, so yeah, what we'll do is we'll again follow a recursive approach here to solve this problem. And let's say I have this whole thing. What you can do is, there is one important thing. You can do a pre-order, you can do a post-order, you can do an in-order traversal. Anything that you want, you can do in this problem. All that we want is we have to follow a certain approach, right? So let's look at this tree. So can you see that these lines that I've drawn in the white, they have certain nodes that are visible to us, and there are certain nodes that are not visible to us. So for every line, we are only concerned about the topmost node, right? So if you look at this middle line, this node is visible to us, and this is the topmost node in this line. Similarly, this node is the topmost node. This is the topmost. This is the topmost. Right. So the approach here is very simple. Let me just write it here. Approach is very simple. For every line, we need the topmost node. For every vertical line. Right. I think this should be clear that for every vertical line, we need the topmost node. And what about the other nodes? These red nodes, they will be hidden, right? Okay. You can look at it the same way that we were looking at the left view of a tree. So when we were looking at the left view, the nodes that are towards the right in this level, they are not visible to us, right? Similarly, in the top side, the nodes that are below in this whole line, they will not be visible to us. They will be blocked by the upper nodes. Okay, so the approach here, I think, should be pretty simple, and this should be understandable. That for every vertical line, we are concerned about the topmost node. Okay, so is this part clear till now? Like, this is the final approach that we will be using to solve this problem. And now all that remains is to actually look at the code and write it ourselves, maybe. Right. Can I have a yes or no if you guys have understood this? Yes, clear. Got it. Great. So yeah, let's devise an approach that we can use to solve this problem now. Okay. So let's look at it here. I mean, I'll be writing more now, and let me use Code Studio only for this. Okay. Cool. So what is our approach here? For every vertical line, we need the topmost node, right? But how will we be, defining these vertical lines? We'll have to somehow define them, right? So for that, what we can do is we can assign them a number. We can assign them numbers like, like you assign numbers on a number line, on a horizontal number line. So we can assign this middle vertical line to be something like 0. For this one, we can have 1. For this one, we can have 2. Sorry. For this one, we can have -1. And for this one, we can have 1. Similarly, -2, 2, -3, -4, and 3. So these numbers will be telling us the vertical line that we are actually referring to. Okay. Now, can you see that? I mean, this should be pretty intuitive now. That if we are at node n, or let's call it node r, or let's call it node root, and if we move towards the left, the value of vertical line will decrease, right? Similarly, if we are at node root, if we move towards the right, the value of the vertical line will increase, right? So what I'm saying here is that if I'm at the root and your vertical line is, let's say, 0, and if you move towards the left, your vertical line will become -1. Similarly, if you are, let's say, on node 2, and if you're on vertical line 2, let's keep it like this. And if you are on vertical line, let's say 2, and if you move towards the right, the vertical line will become what? Will become 3. Okay. So, and now our approach is what? Our approach is for every line. What we've done till now, we've assigned these numbers to these vertical lines. We've come up with an approach. What is the approach? That for every line, we'll pick up the node which is at the topmost level. Okay. Now let us also consider what will be the level here. So let's say if I tell you, if our current level is, let's say, something like 5, and if I move below, if I move to one of the children of the root, let's say I move towards the root left or root right, what will happen is our level will increase by 1. Right? So essentially, what are the things that we are tracking here? We are tracking 3 things. First is our root, the node that we are at currently. Second is the level of this node, and third is the vertical line that it is pointing to, that it lies in. Right? So these are the 3 things that we are concerned. And what is our approach? The approach is that for every vertical line, pick up the node that has the minimum level. Right? Is this part clear to all of you? That why exactly for every, let me just show it here. So our initial approach was what? For every vertical line, we need the topmost node. How do we define this topmost node? We define it in terms of its level, right? So our final approach is that for every vertical line, and we've also assigned numbers to these vertical lines. So these are not like abstract number lines. Not number lines, vertical lines. We've assigned them numbers here, right? So our final approach is that for every vertical line, pick up the node that has the minimum level. Okay. Now, how will we do this? What we can do is we can use any data structure, something like a map. What does this map store? This stores something like vertical line. Let me write it like this. All of this in a map. And how is our map looking here? Map has 2 coordinates, 2 values. So what is our first? First is the vertical line. And what is our second? What we can do is we can sort of store a vector here in the second. Vector of all nodes. That come in this, in this vertical line. Right? And at the end, what we can do is for every vertical line, sort its vector and print the node that is at first index. Okay. So is this making sense? Is this clear? I mean, I'm not sure if you all are familiar with what are maps and what are vectors. So if you talk about Java, a map is a map, same. If you talk about vectors, vectors are nothing but array lists. Similarly, for Python, a map is a map, but a vector is like a list. Okay. So this is our final approach that we've decided. And I know that this seems really very complex. I know this. Why? Because we are, considering every problem with a different approach. We looked at the left view and we considered a different approach. We looked at the right view, we considered a totally different approach. Not, I would say totally, but a little bit different. But when we look at this top view, we are, doing a totally different approach. This is nowhere related to the left view or the right view, right? So what we can do is we can look at the code here. I am not going to code it up myself, but we're going to look at the code that is given the solution. Oh, that's a valid point again, Amit Kumar. Amit Kumar says that, why do we need to store all the nodes in the map when we only need one? So this is a good point. This is a very good point. Instead of storing every node, what we can do is, just give me a minute. Yeah. So instead of storing the second as all the nodes, what we can do is we can, maintain sort of a dynamic thing. What we can do is we can store the node that is at the lowest level. Right? How are we going to compare this? Let's say I tell you that there are two nodes A, B at the same vertical line. So how are you going to compare which is at the lower level? You will simply check which level are we at right now. Can you see that we are concerned about three things here? The root, the level, and the vertical line. So if we have two nodes, A and B, we know that they're in the same vertical line. So what we can do is we can compare the level. If level of A is less than level of B, we want A. If level of B is less than level of A, we want B. Okay, so that was a good point. This is an optimization that we can do. Although I would like to say here is that if you look at it in a very general sense, the overall time complexity would not change. Okay, how will it not change? Because let me just show it to you here. We are already doing an approach that is order of n log n. Why order of n log n? Because we are using a map here. So insertions and deletions both take log n time, and we have n nodes. So for every node, we'll be trying it out, right? So the overall time complexity is already order of n log n, and if I sort the vectors later on, it won't change it. But yeah, that is a fine optimization. Okay, so I think we can look at the solution now. This whole approach should be very clear to you now. Let me just go through it once again. So for every vertical line, we need the topmost node, right? And if we are at a particular node, and if we move towards the left, the value of the vertical line will decrease by 1. Similarly, if we are at a node and we move towards the right, the value of the particular vertical line will increase by 1, right? Similarly, when we talk about the level, if we are at a particular level and we move to any of the children of this node, the level will increase. Okay. So I think where exactly did we cover this? This level part. I don't know if I've written it here. But yeah, this should make sense now. Let's look at the solution code now. I mean, I can code it up myself right now in front of you guys, but it would just take up a very long time. So it is better if we just look at the solution and come to the final approach that we're really concerned about. Cool. So what we're doing is, like I said, in this whole problem, you can do anything you want. You can do a pre-order, you can do a post-order, you can do an in-order. All that matters is that at the end, for every vertical line, we need the topmost node. Cool. So this is what they've actually done in this solution. They've stored a map. This map is telling us that int is the vertical line. Let me copy it here. Okay. And let's write it here. Okay. To store horizontal distance as a key and pair of nodes value and its level as the value. Now, what is our horizontal distance? Horizontal distance is the vertical line number. Like I said, we were concerned about 3 values. the current node, the vertical line number, which is the horizontal distance, and the current level. Okay. And after that, what are we doing? We are just simply doing a pre-order traversal. And in this pre-order traversal, what we're doing is, first of all, this is the base case. We have reached at the end. Reached at the end of the tree. Now, what is this auto x equals to visited dot find h distance? What is this telling us? This is just finding, whether there is already a value at this vertical distance or not. Sorry, the horizontal distance or not. So auto x is telling us what is the node that is present at this, vertical line distance, sorry, vertical line number or the horizontal distance, and what is our current node that we have to compare it with. So if x equals to visited dot end, what does this mean? If you are having a condition that x equals to visited dot end, this means that for this particular vertical line, we haven't encountered any node yet. So if that is the case, we just insert our current node in this, in this map, which tells us that for every vertical line, what is the current node, right? And if there is already a value, this x second dot second is telling us that if our if the node that is present, if its level is greater than our current level. So let me just write it here. If there are no nodes in this vertical line, pick up this node. Or if there is a node in this, compare its level. Compare its level, and if our current level is less than the node present right now. Okay, let me bring it to the next line. The node present right now, we just replace it. Right, and after that, it is very simple. You're just doing this. You're just calling a pre-order traversal. Like I said, if you're moving towards the left, your vertical line number will decrease by 1. But since you're moving down, the level will increase by 1. Similarly, if you're moving towards the right, your vertical line number will increase by 1, but your level will also increase by 1 because since you're moving down. Cool. And at the end, what this is doing is that for every vertical line that exists, it is just pushing these values in a top view vector that they've created. Right. So can somebody tell me if this everything was clear till now or not? If you have any doubts in the top view particularly. Okay, I see no messages. Maybe somebody can respond if I am audible or not. Okay, it is clear. Great. So do you guys have any doubts? If somebody has doubts, then you can ask me. Okay, please explain it again. So which part do you want me to explain it again? Like there was just a lot of stuff that we covered right now. Can you be a little more specific? If you want me to explain everything again, I am free to do it, but I'm open to do it. It would just take hardly 5 minutes to explain this whole thing again. But if there is certain specific things that you could not understand, I would love to know that. Okay, just give me a minute. Maybe I think there is a lot of lag in the chat. So I'll just open this video on my mobile and see the chat. Okay, so explain the whole thing again. Okay, no issues. We'll cover this whole thing again. But right now we'll be doing it quickly, and I hope Coding Ninjas would be providing you with the recording of this whole session. So I'm not going to explain the entire thing again very slowly like I did. So just a minute. Let me see if I have that tree again. Okay, turns out that we've lost that tree, but anyways, we will make another tree. right? Cool. So can you look at this tree here? Just a minute, my mouse is not working. Okay, cool, now it is. Okay, so now if you look at this tree and you draw certain vertical lines on this tree, you want to look at this tree from the top, okay? Just remember this. And if you start drawing vertical lines like these, right? So can you see that for every vertical line that we have, we are only concerned about the node that is at the very top. Why? So let us look at the nodes that are visible to us here. This node would be visible to us. Okay, let me increase the size here. Yeah, now it should be better. This node is visible to us. This is visible. And which are the nodes that are hidden? Just look at the nodes that are hidden. This is the node that is hidden. This is the node that is hidden. This is hidden again. And can you see that the node that is on the top is only visible to us for every vertical line? Right. So this is our entire approach, that for every vertical line, we'll just pick up the node that is at the top. Cool. So now what I'll do is, okay, dry run with an example. Let's just, first explain, let me just explain this approach very quickly once again, and then we can dry run it with an example. Okay, I hope I haven't lost that whole text. Yeah, it is here. So what is our approach? For every vertical line, we're concerned about the topmost node. And can you see that, let's say I give you a route, you are at a particular route, and if you move towards the left, the vertical line number will decrease by 1. And if you move towards the right, the vertical line number will increase by 1. Cool. And similarly for the level, if you move towards the left or the right, your level will increase by 1. Why? Because we're going towards the children of our current node now, current route now. Fine. So this is exactly what we're doing. For every vertical line, we are concerned about the node that has the level which is minimum. Right. So we're using a map for that. The first part of the map just tells us the vertical line that we're referring to. The second part of the map tells us what is the node that is at the lowest level for this vertical line. So how do we compare two nodes? If there are two nodes in the same vertical line, let's say these are nodes A and B. If level of A is less than level of B, then we want this node A. And if level of B is less than level of A, we want this node B. Right? So I hope now the approach should be clear to all of you. And let me show the solution again. Okay, let me look at this. Okay, so can I have a very quick yes or no if now it is clear or not? Then we can do a dry run with an example here. Right, so I don't see any doubts here. So what I'll do is I'll just dry run this whole thing with an example now. Cool. So let's look at this one example. Okay, where is the example here? So do you want me to cover this big tree here? Let's cover this part. Okay, let's cover this. So I think if we cover this tree as an example, everything should be clear after that. And I'm not sure if I can copy this on my OneNote here as well. If I can, that would be great. Okay, yeah, great. So we can do that. Can I draw it? Yes, we can. Cool. So can you see that what are we doing in this whole question? We are, like I said, you can do any traversal. You can do a post order, an in order, or anything that you want. All that matters is that at the end, for every vertical line, you should have the node that has the lowest level. Cool. So let's just define our map right now. What is our map? First of all, let's define the vertical lines. These are the vertical lines. This is 0. Okay, just a minute. This is 0. This is 1. This is 2. This is -1, -2, and this is -3. These are the vertical lines, okay? And so what we'll do is we'll first of all encounter node 1, right? So we'll come to this node 1, and what is the level of node 1? Node 1's level is, let us also define these levels. So the levels are the levels are 0, 1, 1, 2, 2, 3, 3, 4, 4, and 5. Cool. So right now our map is empty. Okay. If we have our map, it is empty. Cool. We first of all encounter this node 1. So what we'll see is that for the vertical line 0, this is in the vertical line 0, right? So we'll see that in the map, there is no node that is present on this vertical line. So what we'll do is we'll just assign this. Okay. So how will we assign? For 0, I have the nodes 1. And what is the level? We also have to keep track of the level. The level is 0. Right? Cool. Now we'll move towards the left because we are doing a pre-order traversal. We encounter node 2. Now what you will see is it is on the vertical line -1. Right? Now since this is on the vertical line -1 and there is no value in the map for -1, we'll push this node. So for -1 we have what? We have 2 and the level is 1. Similarly, we move for 4 and we store it here. So we have 4 and 2. Yeah, the level is 2 here. Now we move to 7. Okay. So if we move to 7, what do we see? What is the vertical line number here? The vertical line number is -1. And what are the nodes that we want to compare? We want to compare these two nodes now. 2, 1, 2 is the node, 1 is the level. And sorry, yeah, we have 7, 7, 3. These two nodes are in the same vertical line. But which node will we pick up? We'll pick up this node 2. Why? Because the level is smaller. So this won't change. Similarly, we'll encounter node 9 and we'll see that the vertical line number is -2. So now which are the nodes that we are comparing? We are comparing 4, 2 and 9, 4. So which node will we keep? We'll keep the node 4, right? Because the level is smaller. Okay. So this will remain as it is. Now when we encounter 10, we'll see that its vertical line number is -3 and we don't have any node. So we'll push it. So we have 10, 10, what is the level? The level is 5. Right. So do you guys want me to try run this completely? I think this should make sense by now, because I don't see that there should be any issue now. This is for the top view, right? Yes, it is for the top view. Yeah. So if you guys have any doubts till now, you can let me know. And yeah, I think we can cover one approach that you can use to solve all these 3 problems that are discussed till now together. Can we just keep track of visited number line and apply pre-order? Okay. So if you keep track of the visited number line and just apply pre-order. Okay. I mean, I am not sure if I've understood that completely, but I'll just give you one example here where your approach might fail. So what you can do is you can consider, dry running your approach on this example and see if it works. Okay. Cool. So let me just show you one example here on which your approach might fail. If you are doing that pre-order and you are keeping track of visited nodes. So what will happen is if you look at this tree, if I've understood what you're saying correctly, what you're doing is you're keeping track of the visited vertical lines. right? So what you'll do is you'll do a pre-order, you'll come here, you'll pick up this node, which is fine. You'll pick up this node, but when you come here, this level is visited. Sorry, this vertical line is visited. When you come here, this vertical line is not visited. So what you'll do is you'll pick up this node, but essentially you should have picked up this node. So I think that approach would not work. Right, Garvit, is this making sense to you? Like where exactly that visited concept would fail? Okay, great, great, great. So I think now the top view, the left view, and the right view should be clear to all of you. If you guys have any doubts till now, let's just first of all discuss these doubts. And after that, I'll give you a very good idea which you can use to solve all these problems. So what I'm doing is I'm just waiting for 1 minute. If you guys have any doubts, you can write it in the chat. And also, like for the people who are interested in knowing which all companies do ask certain these type of problems, then Amazon is when they ask these type of problems very much, and Adobe as well. So the great part here is that if you have understood the left view of a tree, and let's say an interviewer gives you the left view of a tree, and he asks you to just print the left view of a tree, the follow-up question can be to print the right view as well. Okay. And similarly, the follow-up question could be to find out the top view as well. So all these three questions are related very much. If the interviewer gives you the top view, they might ask you as a follow-up question to print the left view or the right view. So all these three problems are related. And also what you can do is for the homework, you can look at the bottom view of a tree. We've discussed left view, right view, and the top view. So you can also try to think about the bottom view. It is very similar to the top view. You just have to tweak certain things here and there, and it will work. Right. So do consider trying out the bottom view as well. Okay. So yeah, I think we can discuss a very general approach that we can use now to solve all these type of problems, and this would be a good approach. So I would like you all to listen to this very carefully. So can you see that for any view of a tree, the part that we were concerned about was what? Can you tell me this one thing that was very common, a concept that was very common in all these three things that we've done till now? One property of every node that we need to keep track of. Okay, I see no answers here. But yeah, so can you see that for everything that we've done till now, top view, left view, and the right view, there was one common thing that we were concerned about. What was that? It was the level of each node. Right. This is something that we were concerned about in all of these three questions. We were concerned about the level of each node. Okay, so let me just write it here. Top, left, and right. So top view, what was our approach? Pick the node in each vertical line, which is at the lowest level. Right. For the right view, pick the rightmost node in each level. Similarly, for the left view, pick the leftmost node in each level. So can you see that for these three problems, the main idea, the crux of all that we've discussed till now is the level of each node. We are concerned about the level. Which node to choose was common. We chose which masks others. Exactly. we chose that node at each level which masks the other nodes. Okay. So let's see, if I tell you that I have a level order traversal of a tree, can you tell me which all nodes will be there in the left view, right view, and the top view? So let's I tell you this. Or let's just make a new page here and we can draw it here. Okay. Right. Now, if you look at this tree, and if you consider the level order traversal, so let's number these nodes: 1, 2, 3, and also just to put it here, this is something that we will be doing iteratively. So if in case your interviewer asks you to do any of these views iteratively, this would be a perfect approach of doing that. Right. So let's look at the left view. So for the first level, what is the left view node that we are concerned about? We are concerned about 1. If you talk about the level order traversal, and if you look at nodes 2 and 3, we are concerned about node 2. For this one, we are concerned about node 4. For this one, we are concerned about node 7. And for this one, we are concerned about node 11. What is this? This is the left view. Right? So let's just remove this part and let's see what will be the right view. Now, if you look at the right view, what are the right views? This is 1. This is 3. This is what, 6. Here it is 10. And here it is 12. Right? So can you see that first of all, let's discuss the left view and the right view. If I do a level order traversal, which are the nodes that I'm picking up? For the left view, I'm picking up the leftmost node. For the right view, I'm picking up the rightmost node. Okay. So let's first of all discuss the left view and the right view. We'll do top view a little differently here. Okay. So I hope this is clear here. Just a quick question: is competitive programming important for getting into Amazon? So Manik, what we'll do is we'll pick up doubts like this at the end. Okay, I'll give you 10 to 15 minutes to ask doubts like these. So can you see that if I do the level order traversal, what will be my level order traversal? It will be 1, 2, 3. Then we have 4, 5, 6. Then we have 7, 8. Let's write it here itself. So if I talk about the level order traversal, we have 1, 2, 3, 4, 5, 6. Okay, just a minute. 7, 8, 9, 10, and 11 and 12. So can you see that if you just do a level order traversal, how do we do a level order traversal? We use a queue, and let me just show it to you how we do it in a queue here. So for level order traversal, let's discuss this on another page. Use a queue, right? So let's say I tell you that in the queue you have nodes of this particular level. You have level 3, and these are the nodes 1, 2, 3, 4. So now if you need the nodes of level 4 in the queue, what will you do? You'll pick up node 1 and you'll put its children here. So let's say its children are 5 and 6. So you'll put 5 and 6. Then you move to 2. Then you move to 2, because in the queue, what do you have? You'll first pop out 1, then you'll pop out 2. So when you pop out 2, then what will you see? Let's say its children are 7. So you'll put 7 here. For 3, let's say there are no children. You don't put anything. For 4, let's say the children are 8 and 9. So you put 8 and 9. And now, can you tell me for this level 3, what are the left view nodes and the right view nodes? Left view will be 1. Okay, let's put it here. Right view will be what? Will be 4. Similarly for this one, left view will be 5, right view will be 9. Right? So isn't this simple now? Instead of learning different approaches for these two different problems, we have a very common approach which can give us both the answers. And mind you, this is iteratively. We are doing it iteratively. Right? So can somebody just tell me if the left view and the right view is clear to you iteratively? We'll then move to the top view. Okay, I'm not sure if this was clear to you guys. If you can just drop in a yes or a no. Okay, turns out one person has understood this. What about others? I'll give you 30 seconds more to decide if this is clear, and then we can jump into the top view, and we'll be doing it iteratively. Okay, so I don't see any doubts here. So what I'll do is I'll now explain the top view to you. And the top view is very similar, okay? There is nothing much here. What were we doing in the top view? We were maintaining a map. What was this map telling us? The map was telling us that for every vertical line, we need the topmost node. And how is the topmost node defined? The topmost node is defined by its level. And since we are already doing a level order traversal, let's put it here. So if we are doing a level order traversal, what does this mean? The nodes in the level lower, or let's put it like this, lower level will come first, right? So if the node in the if the lower level nodes are coming first, do we need to compare them with any other node? Like we wanted this, right? Vertical line comma topmost node. But for if for every vertical line, if I'm already getting the topmost node, do I need to compare it with anything else? Do I even need a map for that? Or can I do it using just like a frequency array, something like that? Do I need a map for that if I only need one node? Okay, so what I'll do is I'll explain this question now. How will you do it iteratively without using a map? Now your overall time complexity would be order of n. It would not be order of n log n. And again, the space complexity would be order of n. Okay, so let's just see how will we do this whole question iteratively. And this is very interesting, okay? So you'll find this interesting. Let's consider these nodes. And let us also draw certain more nodes so that it becomes better. Okay. Yeah. So let's consider this example. Now, what did we say? If we are already doing a level order traversal, can I just keep a vector something like this? I can keep a frequency array. And what will this frequency array store? This will be something like this. We can have minus n minus 1. We can have minus n minus 2, and so on up till 0. Then we have 1, 2, 3, so on up till n. What is this telling us? This is telling us that for every vertical line number, have we encountered a node right now or not? So if we look at this node, this will be for level 0. Sorry, this will be for vertical line 0. Let's number it 1. So for 0, I will be making it 1. And for every other, we can keep it something like minus 1, that this node hasn't come till now. Okay, so let me put it here. Frequency array, and what will this be storing? We'll have minus n. Right, so these are the vertical line numbers. Can you understand that for the number of vertical lines that we can have is at max 2n? Even if we have something like a totally skewed binary tree, we would have these vertical line numbers. We cannot have more than minus n vertical line number, right? And for every index, we'll be just storing minus 1 right now. What will this minus 1 be telling us? This will tell us that this node hasn't come till now, right? And now, since we are doing a level order traversal, what we can do is we can maintain two things here. Two things for every node. We can have the level and we can have the vertical line number. Now for every node, when we're doing a level order traversal, we just need to do one thing. Check in frequency array if this vertical line number has a node or not. Okay. If it doesn't, push my node. If it has, don't do anything. Now, can you see that the time complexity here would be order of n? Because this is like a level order traversal, which is, I would say in time it is order of n. And for the space as well, it is order of n. When a node is popped up, how do we know it belongs to which level? Okay, good question, Garvit. Like I said, when you look at this whole thing, have we discussed? Yeah. So if I say that in the queue right now, there are nodes of level 3. So what I'll do is I'll pop out every node from this queue. Let's say this is Q1. This is Q1, okay? And I decide to, make another queue, which is like a temporary queue. Let's name it temporary. Okay. Okay, it turns out that there is a lot of noise at my end right now because there is some construction going on. So what we can do is, I think we can end this whole session now because there has been a lot of time now. So if I can just quickly cover this out, but it turns out that there is just a lot of noise. So I think we can end it now. If you have any doubts, you can always post them on my Discord server or on my YouTube channel as well. Okay, so I think that was it for this whole class. I hope you guys enjoyed it, and yeah, I'll be ending it now. Okay. Okay, I think the noise has stopped, so maybe we can continue for another 2 minutes. But yeah, if there is a lot of noise, I would be ending it. Okay. So for Garvit's doubt, we were having this queue, right? So we will only be putting nodes into a queue when we've popped out all the nodes for this particular level. So we'll have this Q1, we'll have temp. So we'll keep popping out nodes from from Q1 and we'll keep putting them in temp. And after we've done doing all this, we'll just point Q1 to temp. Okay. So this way you will have all the nodes in your level. You will be storing nodes level wise. Right, Garvit, does that make sense to you? And you guys can let me know if there is a lot of noise at my end, because there is some construction going on at my neighbor's house. Is there any list to master tree? I think Striver has one of the, he also has his playlist on trees, so you can refer to that. But apart from that, you can refer to any sheet like Striver's sheet or Love Bubber's DSA sheet. They have questions that are very important from interviews perspective. So you can do that. Also, if you guys would like to, follow me on LinkedIn or anything like that, I can share my links here in the chat. So this is my LinkedIn profile, and let me also share my Discord server link, because you guys can post doubts here if you have any. Okay, so yeah, I think that was it for this whole masterclass, guys. I hope you all liked this and you got to learn something. So yeah, I will be ending the whole broadcast now. Okay. So yeah, bye bye.